Now, let's look at another sorting algorithm, merge sort, to illustrate the paradigm of divide and conquer. So given an input sequence, let's say we have 8 elements in this case. As a divide and conquer algorithm, merge sort also follows the same 3 steps. So the first divide step, you're gonna divide this input sequence into smaller sequences. So for example, we can divide the input sequence into 2 equal-sized sequences. Let's say first 4 elements be the first group, and the last 4 elements be the second group. And the second step, conquer step, recursively solve the sorting problem. So recursively sort the first 4 elements, and the result is 2, 4, 5, 7, and recursively solve the last 4 elements. So the sorted sequence would be 1, 2, 3, and 6. So that's the conquer step. And the combine step. The combine step going to combine the results of previously sorted subarrays to an entirely sorted array. So let's put these 3 steps here. The divide step, equally partition the array into 2 subarrays. This is trivial because you can find the middle point of an array quite fairly easily. And then conquer step, recursively sort 2 subarrays, which is also not difficult. Here, for this problem, the combine step is a little bit more difficult to think of. We need to merge 2 sorted subarrays into 1 sorted array. So how can we do that? How can we do this efficiently? Let's look at an example first. Suppose we have the 2 sorted subarrays from 9 to 12 and from 13 to 16. And then we want to merge them to be a sorted array from 9 to 16. So first of all, we use 2 arrays L and R to help us. So we put the first subarray to L, and we put the second subarray to R. So you can see 2, 4, 5, 7 is copied to the array L, and elements 1, 2, 3, 6 are copied to the array R. And then we use 2 indices I and J to point to the beginning of the array, and we use the value K to indicate the current position I want. At the very beginning, I compare the first element of L and the first element of R, and I know 1 is smaller than 2, so I should put 1 here. And after that, I increment K, I increment the J. So now I'm looking for the second smallest in my final sorted array. So I compare 2 with 2, and you can pick either one of them. If I pick the 2 from the array L, and I put the value of 2 to the second location, I increment K, I increment I. Now I'm looking for the third smallest element in my final sorted array. So I compare the element of L sub 2 and the element of R sub 2. And 4 is bigger than 2, so I know the third smallest element is 2. I pick this one, so I increment K, I increment J, and so on. So you can do this until you filled up all the locations from 9 to 16. So this is the pseudocode for the process I just mentioned. A is the input array, and there are 3 indices, P, Q, and R. So lines 4 and 5 copies the value to the array L, and line 6 and 7 also copies the elements to the array R. Lines 10 and 11 initialize the 2 indices I and J And then lines 12 to 17 find the smallest element for the final sorted array one by one. If you're interested, you can check the textbook. There is a loop invariant analysis to verify why this loop from line 12 is correct. For this merge function, we know that the for loop start from line 12 dominates the complexity. And here, k goes from p to r, so we know it is linear to the size of the problem. So now let's look at the pseudocode for the merge sort. The input of this algorithm is A from P to R. And then line 1 checks to see whether this input array contains more than one element. If that's true, line 2 divides the input array into two subarrays from P to Q and from Q plus 1 to R. Line 3 and 4 recursively solve these two subproblems. And then line 5 call the merge function to combine the results of these two sorted subarrays. So now let's look at the complexity of this algorithm. So line 2, that's for the divide step, that's easy. So it can be done in constant time, sit 1. And line 3, that's one recursive call, and the problem size is n divided by 2 because we have two equal size subarrays. And line 4 is another recursive call with the same size. So we have here 2 times Tn divided by 2. And then line 5, that's a merge function. So we discussed earlier, it's a linear function. So theta n, we put these three components together, we got this recurrence for this algorithm. Tn equals 2 times Tn divided by 2 plus theta n. So here, 2 is the number of subproblems, n divided by 2, that's the subproblem size, and theta n is the time for divide and combine steps. Now let's see how merge sort is executed. Suppose you're given an input size of 8 elements. So here is the call graph. The initial call is ms18. So you have 8 elements. And then you break the original problem into two smaller problems from 1 to 4 and from 5 to 8. And you make two recursive calls. And then, for example, from the subproblem 1 to 4, you again make two subproblems, 1 to 2 and 3 to 4, and you make another two recursive calls, and so on until you got the subproblems only contain one single element, and you stop. So this is the entire call graph. If you're familiar with recursive functions, this kind of call graph is very common. And the actual merge, however, happens from bottom to up. So here is your initial sequence. The first merge happens with two single elements, and then the result is a sorted sequence with two elements. And then the next merge happens with another pair of single elements, and the result is also a sequence of two elements. So when you have these two sorted sequence with two elements ready, you can merge them and form a sorted sequence of elements. And then again, similarly, when this is ready, you can form to this sorted sequence with 8 elements. Actually, we can have an incremental implementation for the merge sort, and this chart can give us some hints. We know we should first merge the first pair of elements, and then we merge the second pair of elements, and so on. This is because this partition of the subproblems does not depend on the instance. Okay, so you don't have to rely on the divide and conquer steps to generate these small subproblems. So you can implement a incremental approach to perform these merges level by level.